And yeah, it's a really good point that, Steve, about the information repository. There is a fantastic amount of information out there as well, particularly the newsletter and also the Tether materials part of the newsletter, because I write that. Right. On to presentation here. I've got lots of slides, a little bit less time than I anticipated, so I'm going to fly through them a little bit. And don't worry if you miss anything, the PDF of the slides is available for everybody. And if you can't get them from Dennis and Larry and the other guys at ISEC, my email is at the end, and quite happy to take questions by email after the event as well. So, space elevator, you all know that it's a long dangly thing that goes from space all the way down to the Earth. And at the moment, we think it'd probably be on the ocean. And it's a lift that goes direct from the surface of the Earth back up into space again. And we covered all that yesterday. So I'm not really going to go too much onto the structure of the space elevator because I'll be repeating other things. So it's very big. And the key thing I'll be talking about is the material that the tether is made out of. And that's a piece of material 100,000 kilometers long, 100 million meters long. And you can see the scale of the thing here. And this was a graphic that was commissioned by Pete Swan as part of Galactic Harbour Associates. The reason I've put this in, it's looking down on the space elevator with a climber coming up. And this is one of about the only image of a space elevator that's actually technically accurate that I've been able to find. A long, thin, flat ribbon that's metallic looking, and I'll say more about the appearance of the tether a little bit later, because there's information in this talk which is only a few weeks old. So some of the stuff other people familiar with my talks will have seen before, but there's fresh new material in here as well. So tether material problem, you all know this one. Imagine you're standing on the edge of an infinitely high cliff and you are a superhero, so you can hold tons of material, and you start lowering a super strong cable over the edge, and the material that dangles over the edge eventually acquires more and more weight pulling on it until eventually the cable breaks under its own weight. And that is effectively the problem we have with the materials that are currently available for the space elevator tether. The material needs to be super lightweight and super strong. Strength is measured in pascals, as you all know, and today's super strong materials such as Kevlar have strengths of around about 4 gigapascals, something like that. Carbon nanotubes at the moment have been going up to about double that, but carbon fiber has gone up to double that. But the space elevator tether requires an order of magnitude stronger, so we're looking 60 to 100 gigapascals. So what are the candidate tether materials? Well, just go back again. We have flat stuff and tube stuff. So the flat stuff are 2D materials such as single crystal graphene and single crystal hexagonal boron nitride. Now, Rod Ruoff talked about these in his talk yesterday. And also we've got their nanotube equivalents, which are the same material but rolled up into a cylinder, a bit like the inside of a toilet roll, and just very, very long. Now, if these materials are kept as a single molecule for the entire length of the tether, then you can take full advantage of their super strong strength. So you can see here, each one of these candidate materials, we've got the carbon-based ones, carbon nanotubes and graphene on the left, and the boron nitride materials, which have boron and nitrogen in them on the right. And they're all well in excess of the strength required. So these are the 4 primary candidates. Interestingly, yesterday, Rod Ruoff also talked about single crystal diamond. But because nobody's ever made single crystal diamond in anything like a useful length, I'll park that for the moment, as Rod did, because we're looking at things that can be manufactured. And so how do we actually go about making these things? Well, the super strong materials can be made in the lab. Rod yesterday in his talk talked about epitaxial growth of materials, graphene and HBN. What that word means is growing something on the surface. And here you can see that we start off with something called methane gas, or methane as you'd refer to it in America. This is the gas that comes out of your pipes at home or is dug out of the ground, and it contains carbon with hydrogens on it. and you bring it close to the surface of a metal catalyst around about 1,000 degrees, and then that allows the carbon to come off, the hydrogen to come off. The carbon lands on the surface, and the metal acts a bit like a dating agency for carbon atoms, and they self-assemble in this hexagonal chicken wire form as a monolayer or sometimes multi-layers, depending on how you get the reaction conditions on the surface of the metal. Carbon nanotubes, they're grown by a similar but slightly different method where the carbon is dissolved into the metal catalyst, and these are quite complicated catalysts, but basically a forest of fibers will grow out from the surface. In both cases, the metal acts as a catalyst for growing either the flat stuff or the tubes. And I'm going to concentrate at the moment on graphene because the manufacturing of graphene is more mature than for making longer and larger scale sheets than it is for nanotubes. And an important point here to note about making graphene is that graphene is actually two types which are both called graphene, but they're very different materials in some ways. We've got the graphene is currently manufactured in terms of powders, and this is an additive that's added to other materials. There's a whole talk I could give about that. But what we're talking about here for the space elevator is what's called CVD graphene. This is what Rod talked about yesterday. Here's a picture of a piece of copper foil that's come out of that CVD process. It's been heated up to 1,000 degrees. It's got graphene on it and then allowed to cool. And can you see here just at the edge, you can probably see my mouse moving. You see this darker strip down the edge of this sample here. That is the base material of copper. And then the rest of it, can you see there's a slightly more silvery coating on the surface? What you're actually looking at there is a one atom thin coating of graphene on the surface of the copper. This is the only photograph I know in the world which shows this. So I know that because I took it when I saw the material at the Geek. More about that later. One other thing, graphene can also be classed as polycrystalline or crystalline. If it's single crystal, then the graphene, the chicken wire pattern is uninterrupted across the entire boundary of the material. But there's also a term polycrystalline, which means that there are grain boundaries in here, and these are 5, 6, 7 membered rings, 8-membered rings sometimes. And you can see here that I've outlined these in red on the sheet. We originally dismissed polycrystalline graphene as being too weak for the work, but over the years of working with ISEC, we've discovered that provided the boundaries connect up, that's what Rod Ruoff refers to as well stitched together in his talk. Provided things are well stitched together and no vacancies, the polycrystalline material actually is quite strong. So we're going up to nearly 100 gigapascals compared to the 130 for graphene, single crystal graphene. And this is how it's made. So you have this is a roll-to-roll process developed by MIT originally. This is a horizontal one where the copper foil is taken through a heating zone, and then gradually the methane is introduced and the graphene grows on the copper, and then it's reeled up. You then dissolve the copper, or you peel off the graphene from the surface, and that can be stacked up to make freestanding graphene sheets. A few years ago, this would be thought to be science fiction, but this is now routine industrial process, at least at the lab scale. And here you can see one. So here you can see on the left-hand side over here, this is the Graphene Engineering Innovation Center. This is partly where I work. And we're looking at one of the laboratories on the ground floor just inside here. And those of you familiar with the people at ISEC will recognize Dennis, our president, who's just been on, John Knapman, who's coming on after me. And John, I'm aware I've got 5 minutes. And this is my colleague, Rob Wheeldon. The chap on the right-hand side is James Baker. He's the chief exec of the Geek. Now, we got taken into the CVD laboratory, the Chemical Vapor Deposition Laboratory, and were shown this Extron machine here. This is one of 2 CVD roll-to-roll machines in the world. I'm not allowed to see what Dennis and John were looking at through this door here. I'm not allowed to photograph it, but you can just see a copper roll coming down from the top here. It goes through a vertical tube furnace and then reels up underneath, and in the process deposits graphene on the surface of the copper. This system can make up to 50 graphene in up to 50 meters long as a monolayer and speeds of meters per hour. They won't tell us exactly how fast it goes, but we do know it can make 20,000 square meters of graphene per year. that's in operation at the geek and making material. And this is something that you won't have seen before. So I took this a few weeks ago when Dennis came to the geek, and this is graphene that Extron machine produced. Can you see the square here on the glass inside, slightly darker? That is three-layer graphene that's been made by that machine you've just seen and stacked up one atomic layer on top of the other. It was done by a dry transfer process. So the graphene was separated from the copper and then stacked up onto the sheet of copper there. And I used Photoshop or a Photoshop equivalent called Affinity to measure the brightness and discovered that it's not quite what the geek said it was. It's probably a few layers less. And we think the reason for that is because the dry transfer process tore some of the layers of graphene. You can look at the detail a little bit later on that one. I can answer questions later, but I need to move on. There are industrial manufacturing processes. LG has one that can make graphene up to speeds of a meter a minute and lengths of a kilometer. Charm Graphene are already making at speeds of 2 meters per minute and lengths of up to a kilometer. And this is what Charm Graphene make at the moment from their process. You're looking here at 30 atomic layers of graphene, freestanding graphene. There's nothing supporting it in that frame apart from the frame around the outside. And you're looking through 30 atomic layers of graphene there. And that's quite an impressive feat. I'll pass over this. This is just comparing graphene with carbon nanotubes. And so what we're working on here is so new that the language is evolving. More than 10 layers of graphene in the graphene community is called graphite. And that is a technically accurate way of describing it. But when we're looking at a new material, which is this large area graphene, which is layered up on top of layer on layer on layer, we're calling this single crystal graphene superlaminate to distinguish it from graphite. And this will give you an idea. We've got graphite down here at this end, which is made of lots of little stacks all jumbled up. There's something called HOPG, highly oriented pyrolytic graphite, which is more ordered. And then we've got the graphene laminate with vacancies. That's probably what you saw the material, that three-layer material at the geek. That's probably what that is. This is the well-stitched together graphene laminate material with no vacancies, still polycrystalline. And over here, we've got graphene superlaminate. And this is an increasingly strong material. Two final hypotheses very, very quickly. So back in 2022, we said we should be able to spot weld graphene and in the process make something called hexagonal diamond or Lonsdaleite, the strongest form of diamond in the world. And it's never been made on Earth. You usually find it in meteorites. A few weeks ago, that was made. So a team in China have actually spot welded graphene superlaminate, and they took a single crystal of graphite and squished it, and they did indeed form super diamond Lonsdaleite. So we know that a tether material can be spot welded now, and that's been proved. And that's what the spot welding looks like. And then finally here, in the December 2020 issue of the newsletter, we said that graphene superlaminate should have a mirror-like appearance and be silvery and mirror-like. And Rod Roff's team, again, this is just a few weeks ago, less than a month ago, produced a paper in Nature showing that multi-layer graphene, this graphene superlaminate, does indeed have a mirror-like appearance when it's made as large grain graphite films. Nice to be proved right. That's roughly a little bit more that's going on there. So that's what the space elevator tether will look like. Perfectly smooth mirror, like flat ribbon, 100,000 kilometers long, thinner than aluminium kitchen foil, and that would rise straight up out of the sky, disappearing out of sight. And that very thin, almost fragile looking material will support climbers of tens of hundreds of tons in weight. So that's me done. Oh, just hopefully squished enough into the right time.
You have another minute.
Questions perhaps, Dennis? I'll stop sharing.
Okay, so please put up your virtual hands and we'll try to call on you. Jim.
Yeah, Adrian. Since it's a mirror-like surface, what do you anticipate the solar radiation impact on the tether would be?
Oh, that's a good question. It will reflect about about 20% of the light, 10 to 20% of the light that's shining on it. And the solar radiation will heat up the graphene layers, but graphene transmits heat at 13 to 20 kilometers per second. So once the tether heats up, it will ship the heat away to other parts of the tether very, very quickly. So
Right, but the transfer would be along the surface of the graphene instead of across the layers of the graphene.
it's a
So
very
what's
good
the
point.
heat transfer through the layers? So you'd have a shaded side versus a sunlit side.
Very good point. Yeah, so you have one side's expanding slightly more than the other side. That's a very good point. And the thermal conductivity in in plane is 1,000 times better than the thermal conductivity across the plane. So yes, you're right. You will get sort of different layers towards the sun will heat up slightly more than the layers inside. Graphene will expand up to 6% of its length, depending on how hot it gets. So the layers can slide over one another unless they're spot welded together. It's a very good point. That I think. Tell you what, I'll look into that a little bit more detail, and maybe that'll become a future newsletter article, just
Yeah.
showing how the heat profile will actually manifest itself in sunlight.
Right. In Edwards' study, he anticipated that the ribbon would have a crescent shape to it. So the sunlit side expanding faster than the shaded side would help form the crescent, except 6% might yield it curling entirely upon itself, forming a tube instead of a crescent shape.
Yep, unless the layers slide over one another, in which case you wouldn't have that too much of a problem. But also, Brad was working on carbon nanotubes. That was his assumption because
Right,
graphene hadn't actually been isolated when Brad published his survey in
right,
2003. Yeah.
right. But if it's not stitched together, then we have problems of the traction wheels peeling only being supported by the outer layers.
That's a very smart question. Yeah, one which we discussed in that newsletter article in 2022. So
Yeah.
it's called Slippage of Layers in Graphene, and you'll see that we addressed exactly that
Okay,
problem back then. Yeah.
thank you.
All right, thank
Les?
you.
Yeah, I was just going to comment about the heat transfer through the ribbon. The thermal diffusion, like it's so thin that the heat will transfer through very fast. It's a small fraction of a second. I don't have the numbers handy here, but I would not worry about difference in temperature between the two sides of the ribbon just because of it's so thin.
Brilliant. Cheers, Blaise. Thank you.
Other questions, comments? Yeah, I'll just say that we've had over the years meetings about what we need for the strength and properties of the tether, and Adrian always thought that spot welding could be done, and now in fact it's done. So it's gratifying to see this stuff actually happening.
Great. Thank you. I'll switch off and hand over to John.